Hi everyone, and thanks for joining us for today's webinar, which is a step-by-step guide to slope stability analysis with LimitState GEO. I'm Tom Pritchard, the host for today's session, and I'm joined today by our speaker, Professor Colin Smith, who is the LimitState GEO product manager. During the webinar, Colin is going to be guiding you through the process of setting up and analysing a range of slope stability problems with various real-life considerations using our geotechnical software, LimitState GEO. The main section of the webinar is going to run for approximately 20 minutes, and this will be followed by about 5 minutes at the end for questions. You can post these at any time using the Q&A panel that's present in the interface, and we'll try to answer as many of the questions as we can in the time that's available. But this isn't always possible, so we do apologise in advance if we're unable to get to yours during the webinar itself, but we will follow up after with any answers via email. So without further delay, I'm going to pass you over to today's speaker, who is Professor Colin Smith.
Well, thank you, Tom, for that introduction. So by way of introduction to the software, if you're not familiar with that, LimitState GEO is a fully general ultimate limit state analysis program designed to identify critical collapse mechanism for any problem type in the form of a slipline mechanism, as you can hopefully see in these examples. What we're going to look at today in today's short webinar is a problem of a road widening on a slope, and we'll look at various details of that as we go through. And we'll kind of wrap up with a little explanation of how the program works and gets to its solutions. So, problem definition. We're going to be looking at an existing road on a layered slope to be widened. A fairly largish surcharge, 40 kilonewtons per meter squared, we're going to assume is acting on the road. And we're going to try and widen the road to this extent. Assume that if we just try to widen it without adding this small concrete or gabion wall system, the slope would be too steep for stability. So we're going to assess the stability before and after the widening solution. We're going to assume that our model geometries are available as DXF files, so we can import those, and the soil properties are as listed below. Not expecting you to remember all of those, but these are the ones that we'll be putting in there. So the road base is the kind of black material at the top here. The made ground is the darker brown material, and then we have the existing slope and clay stratum. And if we are going to model this concrete or gabion wall, we're going to assume conservatively that we've just got half the adjacent soil strength available on the interface. So we'll see how we model those various aspects a little bit later on in the presentation. Before we just get into the modeling and the software, just say a little bit about the ultimate limit state analysis of slope stability problems. So essentially, there are anything that you analyze or you design ought to be stable, hopefully, and there'll be some distance away from collapse. So we need to have some way of determining how far away from collapse we are. And so normally we need to perturb the system in some way. Now we can do this in two general ways. One is to ask a question: if we have an existing load in the system, how much bigger do we have, or by how much do we have to increase that load in order to achieve a collapse state? So in this case, if we talk about that surcharge or that assumed traffic loading on the road, how much bigger do we have to make that before this thing will collapse? And that factor is what we'd call the adequacy factor on load, or factor on load. And that can be applied to external loads or indeed to self-weight of materials in the software. The other way of doing it is to say how much do we have to reduce the strength of the soil in order to cause collapse, or by what factor F do we need to reduce that? And this is what we call the adequacy factor on strength of the software. And this is somewhat synonymous to strength reduction in finite element analysis, and perhaps is more suitable for slope stability problems where sometimes you don't have an external load, and it's certainly for frictional soils, it's far more intuitive to look at the factor on strength as your margin of safety away from collapse. So that gives a little bit of background. We'll show how to do that in the software in just a moment. So, oh, sorry, one last slide just to wrap up. So this adequacy factor that we obtain, fairly simple rule of thumb and fairly obvious. If the adequacy factor is bigger than 1, then your system is stable. And if it's less than 1, the system is unstable. And if you're applying a factor on load, generally it should be applied to any unfavorable load in the system. And in general, it's going to correspond to a global factor of safety or an over-designed factor if you're applying partial factors, such as from the Eurocode. So it gives you that extra margin of safety over and above the Eurocode factors if those are applied. So we'll have a look at the software now and see to set up that problem. So this is standard window that you get, various buttons to the top, the left, and various explorers available. I will talk through some of those details as we go through, but as it's a short presentation, we're not going to have time to do that in detail. So what I'm going to do is import a DXF file. So we go import geometry, and got it already set up. You get a dialog box which allows us to move the origin, etc. I'm just going to click OK to the defaults. There's the main geometry. It's also got some construction lines. I'm just going to clear those, right click and clear. And that gives us our basic geometry. We then have to basically add in our soil properties and so on. So I can use tools, create new material. Generally, I'm going to be creating soils here, so they're all come under the category of more cooler materials. There are a range of other materials that you can create, but we'll stick with those. So the first one is going to be the road base. So I'll just give it that name. I need to spell it correctly and make that one black. Now we can choose as whether the material will behave always in a drained manner, in an undrained manner, or whether we can switch from one to another according to whether we're doing a long or short-term analysis. Here I'm just going to pick always drained, and the properties we had in the PowerPoint before were C-10, Phi-45, the dry unit weight of 18. There is provision to put in saturated unit weights, but we're just going to deal with dry problems in this short presentation, so I'll just stick with the default value for that. So that goes in, and you'll see that that thing appears in this what we call the Materials Explorer here. A lot of built-in default materials for quickly building models where you just want to get a sort of feel for a problem and you haven't got any detailed site investigation data. And what we can do is I can just use drag and drop that into the area that I want. And then I can repeat the process. So very quickly, I'm going to go for another more cooler material. Put in the made ground. Change the color. We'll go for that one. This one again is going to be drained, and we've got a Phi-40 and a unit weight of 18 again. Okay, and that's going to go in there. And then we have an existing slope. You can also use a right click within the Materials Explorer to create a new material. Again, we've got the existing slope. That one is brown, and again, that one will take as drained, and that's got 2 effects. Okay, and we can just drag that over onto these areas. And then the final one we want to make, again, I'll just right click here, new material, again, more Coulomb. So clay stratum. So this time we're going to assume that is undrained. So we're basically going to restrict ourselves to short-term analysis here. So clicking that undrained, only the CU value then is available for entry. So that's going to be a 95, and the unit weight is 20 for that. Okay, and so that's our geometry and material setup. It is possible to save standard materials or export the material properties and import them from one problem to another if you're dealing with the same site. We now have to put the surcharge load on. So any boundary I click on, its properties appear in this window on the right, the property editor. So if I expand this box here, I can see loads. I'm going to take this as a variable load. It's a normal load of 40. And we can set its loading type. I'm going to set that as unfavorable. It's an unfavorable load. So these are kind of Eurocode designations. So that's our surface charge put in, and then I need to put in some boundary conditions. So along the right-hand side, I have fixed boundaries. I can click on these one by one, or I can hold the control key down as I'm doing now and select several at a time. And I can, again, its properties appear here. Common property I'll set to fixed, so that appears as fixed. And I can do the same again down here. And again, we get fixed. And the same again over here. And I'm zooming in and out of the screen just using the mouse wheel in this case. If I press this button up here, that just rezooms back into the problem. So essentially, I've set the problem up now, all the boundary conditions. We can choose between doing a factor load or a factor strength analysis. As I discussed earlier in the PowerPoint, we're going to go for factor strength here. And what I'd also like to do is just automatically apply Eurocode factors. Now, for slope stability problems, generally the only one that makes sense is design approach 1 combination 2. So I'm going to put those in. So the variable and favorable action is going to get scaled up by 1.3, and our material properties are going to get scaled down by the numbers. Click OK to that, and then we're ready to go. So I just click the solve button here, and the system will iterate a little bit and find the factor and strength. So we get a slope failure here. Actually, that doesn't seem to have done what I wanted. Just try that again. It's not a factor load. Sorry, that was how much bigger do we have to make the load on the road to cause collapse? That was a factor of 4. We have to make it 4 times bigger to get to collapse. This is the quantity I'm looking for here. So essentially, we're getting a fairly shallow slide, and the software is telling us that I can animate that actually just to see what happens. We're getting that kind of sliding failure. And if I click on the solution here, it tells me what it's doing. It's basically saying, here are my characteristic values of the properties. Here are the design values scaled by design approach 1 combination 2. And I have to reduce them further by a factor of 1.43 before I get to collapse. So I've got a fairly healthy safety margin over and above Eurocode here. So that's a quick overview of just the initial stability analysis. And you can see the mechanism is basically a whole sort of wedges, effectively. It's basically an optimized wedge analysis displayed as a slipline mechanism. Now, what we wanted to do was look at the widened slope. Now, I can import the DXF for that, but that's just going to take a bit of time. So what I'm going to do is pick an already partially built model. So we just assume we've done the DXF import as illustrated before, but I put in most of the materials and I've created most of those. So I've got made ground here. Again, I can just drag and drop that where I want it to be. So we're going to assume that the made ground is going to extend down to this little concrete wall, Gabion wall. I'm going to make my Gabion wall out of concrete. So we've got a built-in material here called concrete, which I'm just going to drag and drop onto the blocks. And that's pretty much it. But what we need to do is deal with the interface properties. So on the boundaries here, we're going to assume that the strength of the material is only 50% of the adjacent soil type. So I've already created one or two of these. So here is the an interface between the existing slope and the concrete. And what we use here is what's called a derived material, which we specify a parent, which is effectively the existing slope material. And then we specify factors here, which are half, to say that the properties of this material are always 1/2 of the parent material. So I can drag and drop that onto the relevant locations here and here. I then need to create I'll just demonstrate creating one of these materials for the made ground. So here I'm going to select the more Coulomb derived material and call it the made ground interface. That's the same color as the other one. I'll do that color. So the parent material will get a drop-down list of materials. So I just want that one to be the made ground. And again, we just put in these multipliers at 1/2. That's fairly conservative. Put them there, and then I can add them in. Now, I've got 3 boundaries here. I can either drag and drop, but I can also do it by selecting, as I did before, holding the Control key down, just clicking with a mouse. And then you can see the properties appear up here. If I click on this box that says no materials assigned, and click on this change button, you can see I get a whole set of materials available. And what I want is some made ground. So if I just tick that box, I'll get the that material, and then you can see that that has been assigned. Now, the last thing to do is I've got concrete blocks sat on each other. Assuming they're just sitting on each other and they're not actually bonded together, then I need to give those an interface. So I've made a concrete interface, which has got a friction angle of 38 degrees, and I'm going to drop that on here. But also, if I have concrete blocks sat on each other, they might be able to tilt, and so it's quite useful to put in what we call a no tension material, which effectively allows you to specify limiting compressive and tensile strengths. If we set the tensile limiting strength to 0, it means no tension can be sustained. And that basically allows rocking behavior. Probably won't happen in this case, but we put it in anyway. And I can click just add, and that combines the 2 materials. So I have a frictional material that allows sliding, but I also have a material that would allow rocking and hinging, essentially. So that is my model now set up. And I should then just be able to solve that, and just click solve and see what happens, see what the analysis tells me in this particular case. So it's decided I'm going to have a small slope failure here, and actually it's going to slide along the base of the concrete here. So actually that weak interface has probably not done me any favors, but I'm still a factor of 1.26 over and above the Eurocode factors. So I've got a decent, healthy margin of safety there. If I were to take this property out, I can click again on here, change, and just untick it. If there isn't a material specified on a boundary, then it just takes the properties, the property of the weakest material that's adjacent to the boundary, which in this case will be the existing slope. If I redo the analysis there, you can see that I actually get a longer slope failure and the result come out a slightly higher margin of safety. So actually increasing the friction there, putting a key in might be useful on the base of that wall. Okay, one other thing I should point out here, this mechanism is now touching the edge of my model domain. This is probably an artificial domain boundary, so you will get unrealistic results if that happens, and you would need to extend it outwards. But hopefully that's given you an illustration of how we can build some slope stability problems and how easy and quick it is to do the analysis and have a look at the results and play around with a few parameters. So we're going to shift back to the presentation just to wrap up. So all that analysis that was carried out by the software is undertaken using what's called a discontinuity layout optimization procedure, which provides rigorous upper bound plasticity solutions. And those are optimized to be very close to the true solution. Very simply, how this works is I've got a simple rectangular domain of soil here with a surface surcharge and a fixed boundary to the left and to the base. What we do, it's not a finite element method, it's a method where we populate the domain with nodes. This is a 4x3 set of nodes, and we connect every node to every other node with a potential slip line. We then use optimization, very powerful optimizers, to pick out from that rich set of possible slip lines the set that form the critical collapse mechanism. In this case, it's a very simple mechanism involving 6 lines out of our original, I think, 66 possible connections that we have. Generally, we're going to be solving problems with hundreds of nodes or thousands of nodes and millions or tens of millions of potential slip lines, and those can solve in a matter of seconds generally on modern computers. The examples I was showing, we're typically modeling with 500 nodes. Generally, we might model with slightly more, but just for the purpose of illustration, I'd be looking at that. But the accuracy will depend on the number of nodes that you employ. How does this relate to sort of conventional slope stability analysis software? So a lot of conventional software is based on the method of slices. That was developed quite a long time ago to provide a simple hand calculation method that approximated the mechanics of slope failure fairly well. That has now become the basis of many software solutions. But generally, it presupposes some kind of failure mechanism, e.g. a slip circle, and makes some assumptions about what the forces are in each slice. And that can sometimes skew the solution in a certain direction. With discontinuity layout optimization, the LimitState GEO software basically searches all possible failure modes, not just slip circles. It doesn't have to make any assumptions about interslice forces. It just has to satisfy the mechanics of yield, and there's no need to specify a solution type or entry-exit points or centers of rotation. That's all. You can just avoid that entirely. It is, however, useful just to see that LimitState GEO does give similar results for fairly simple slope stability problems where it typically is pretty much a slip circle. So here's just one example of a 2-layer problem. And we've put in a scenario for a dry soil, one where we've got water table at the surface, and one where we've got a surcharge and a seismic load. And you can see that effectively the solutions are all very close. So for simple problems, the slope stability software and LimitState GEO are going to give the same answers, but where you've got more complicated geometries, the LimitState GEO software gives you that much greater degree of power to just pick out the critical collapse mechanism. Okay, so that wraps up our webinar. Just a quick summary. So hopefully you've seen that we can quickly identify the critical failure mechanism for any slope geometry, stratigraphy and loading. No need to specify entry and exit points or solution method or interslice force functions. We can do what-if type analyses, playing around with parameters to see what happens. And the software will search all possible failure modes within that domain of nodes that you've specified in the problem every time you solve. And hopefully you've seen that it's very easy to use and you can use straight away. Hopefully you see we can import DXF files, build our problems pretty quick, solve in one click and apply partial factors, just again, very straightforwardly. And as I've said right at the beginning of the webinar, we can use the software to solve any problem type, and not just slopes. We can deal with retaining walls, sheet pile walls, reinforced soil, etc., etc. Okay, that wraps up the presentation, and we'll just move on to questions. Okay, so we've got some questions. One is asking what happens if we have a patch load set back from the crest, but often we just see a shallow failure on the surface of the slope. It's difficult to assess the more deep-seated failures, whereas other software allows you to check slip circles through a specified point. Can we do that with the software? So the answer is we can't do that directly with software. The software is designed to pick out the most critical collapse mechanism, and that's what it's doing when it finds a very local shallow failure. Essentially, that means that either that is what would happen in your real site, but if you actually and that any other failure mode is clearly going to be less likely, so you're going to have a higher margin of safety. So at least it's going to give you a lower bound on the margin of safety that you have there. But if you actually want to see what those mechanisms are, generally what we advise is that you effectively strengthen the soil near the surface to suppress that local failure mode. And so that load can then get transmitted into the deeper layers and initiate that bigger slope stability problem failure mode. But it's something we have looked at, but it's to allow you to pick individual slip lines basically negates the functionality of the software, which is to automatically find the critical failure mode. And as soon as you try and restrict that, then it becomes very difficult to kind of control the problem definition. So I've got a question: can a detailed output describing the adequacy factor be exported in any other way from a screen grab? So I didn't have time to show it. The software does produce a report, but at the moment that particular summary is not present. But we will make a note of that, and we are in fact in the process of doing a significant update to the software, which we hope to release later on this year. And so we will definitely feed that into the discussions on the specification of new features. And again, if you're a user of the software or you like the look of it, and there are things that you think you'd like it to do let us know. And we obviously try and incorporate those when we can. Another question: is the adequacy factor true or false on soils important when assessing factored loads, or is it only related to surcharge loads? So that is important. Let's just bring the software back. So I didn't have time to talk about this, but if we're doing a factor load analysis, so that's with this setting, you have to tell the software which loads you want it to increase. Now, it may just be one load. So this load, I've got this setting called adequacy true, and that means we're telling the software increase that load to get to collapse. And there's a very useful feature in the analysis here called diagnostics, which tells you what's going on. So here it says adequacy is applied only to that boundary load. And if you click on there, it will highlight it for you. So when we solve in factor load mode, it's basically going to increase that surface load until we get to failure. And here it's saying we've got to make it 4.5 times bigger before we get to collapse. I think the question was, is it only relative to surcharge load? So you can apply adequacy to more than one force or loading, but also the self-weight of material. So if I wanted to include the self-weight of this backfill, I can set this adequacy to true. And again, if I look at the diagnostics, it's now telling me there are two things for that applied. And if I solve, what it's going to do is increase that surcharge and the weight of the backfill. And in fact, it's actually going to fail my little concrete wall because it's not that strong, just by a wedge failure in this particular case. And so what is happening is that I'm increasing the weight of the backfill by a factor of 3. So it's going up to 60, which is highly unrealistic. But those are combined. So yes, they do. It does actually matter. It's not just surcharge loads that count. Okay, unfortunately, we're out of time there. We've got we have quite a range of other questions, which we will answer in due course individually. But I'm going to leave it to Tom to wrap up there. Thank you very much for your attention, and I hope you found that useful.
Thanks, Colin, and thanks to everybody for joining us today. We do hope that you learned something new and useful about the software. If the webinar has prompted any questions, like Colin says, please do get in touch with us. You can do that via email on info@limitstate.com, and we'll be more than happy to help. Obviously, like Colin said, we do have a number of questions that have come in that we will try and answer over the forthcoming days. If you'd like to watch this webinar again, or if you think you might know somebody who would be interested to see it, then we'll make a recording available over the next day or so on our YouTube channel, which is LimitState Software. And we'll email a link once that's available online, and also post it up on our LinkedIn page. You might also be interested to know that there are a number of other scheduled webinars this year that will be dealing with LimitState GEO and its application to other problem types. So do look out for the event notifications that we'll send out via email, as well as posting on our website and on the LinkedIn page as well. So that's it. So thank you all for joining us again, and we do hope that you can join us for one of those future sessions. Goodbye.